So let's begin our discussion of magnetostatics. We're going to start by looking at forces on charges, those that are moving. And so we'll start with looking at forces on current carrying wires. And so we'd like to explore what happens when charges move. And if charges are moving at constant velocity, then we're talking about magnetostatics. So generally the B fields, the magnetic fields, are not changing in time, and particles, at least their speed, is constant. So let's start with just the simplest case to get us a feel for what's going on. Suppose we have two parallel wires shown here, and current is flowing in the wires. So that means that charge is moving, and that's really important. The wires are neutral, so there is no net electric force between the wires. So let's get here where we have the current flowing in the same direction, and here we have current flowing in the opposite direction. If we look at what happens experimentally, in this case here, where the currents are flowing in the same direction, we have attractive forces between the wires. So if you actually had this set up, what would happen is this wire would want to move this way, and this wire would want to move this way, and so that would show you that you have that attractive force. When the currents are in opposite directions, like I show here, then the wires repel. They're basically pushed away from each other. So that really is telling us something about the interaction, and of course the magnetic fields are what's causing this to happen. So for example, the magnetic field due to this current is operating on this wire, this charge that's moving, and vice versa. So this moving charge here creates a magnetic field which interacts with this wire. And the same goes for the two wires below. The force that's responsible for the effects of these wires being attracted to each other and these wires being repelled is due to the magnetic force. So the magnetic force acting on a moving charge is defined in terms of the magnetic field. And the equation for that force is this one right here. This is the charge that's moving in the magnetic field. This is the velocity of that charge. And of course this is the magnetic field. And the force is expressed as a cross product of these two vectors, and it shows you that the force is in a direction which is going to be perpendicular to V and perpendicular to B, because that's true of the cross product. Let's take a case of circular motion in a B field. If you have a charge that is moving in such a direction that it's perpendicular to the B field, it will travel in a circle. And so we want to show that. So consider the case where the B field is into the page and the particle has this velocity v, and so therefore if you take q v cross B, you will get the force in this direction. So use the right hand rule to take V into B. So if you wrap let me just draw it. Here's B that's supposed to be into the paper. So you're wrapping V into B, and with the right hand rule your thumb is pointing towards the center of the circle. So let's review uniform circular motion. And so the important relations are that the speed of a particle moving in a circle is just simply the angular frequency times r. So V equals r omega, or omega times r. The velocity for circular motion is given by this expression here, where omega is a vector which is related to the direction of the motion. Basically it's the right hand rule again, that if omega is the vector, omega is pointing out of the paper, this would be the direction of the motion. So omega here is oriented along the axis of rotation, And to find the acceleration, we just take the derivative of the velocity with respect to time. And since this is a product, a vector product of these two quantities, we have to use function of a function. So the acceleration then is the derivative of omega cross r, and then omega cross the derivative of r. So for uniform circular motion, this vector omega is a constant. So the acceleration that is occurring here will just be a constant, where except we have to take the cross product to get that acceleration. And so what we're doing then is assuming that this term here is 0. So that's how we're getting this expression, because omega is a constant, and then we're left with omega cross v. So that's where this comes from. So let's let F be the magnetic force, which we've defined as this value here. And so the question, first of all, is for velocity as shown and b into the paper, is F in the right direction? Well, we've already gone through that. It definitely is in the right direction. So let's look at the acceleration in terms of this force. The acceleration will be force divided by mass. And so putting in the value of the force and divide by m, we get this expression here. So again, we have acceleration that's going to be proportional to that cross product. So turning this cross product around, we would have the acceleration is minus q over m b cross v. And the reason for doing that is because we can now compare the two equations for A, because we want v on the right, and so you can see that the omega vector is equal to this quantity right here. So it's minus q over mb, omega equals minus q over mb. So if we go back to what I was saying in terms of the direction of omega, omega was out of the paper or page, b was into the page, so that minus sign is in fact correct. So here's the equation again. Let's go to the magnitude of omega. That's equal to the angular frequency, which is just 2 pi f, where f is the frequency of the circular motion going around. So f basically is the 1 over the time that it takes to go around the circle. So the magnitude of omega c is equal to q over m times the magnitude of b. Has a particular name. It's called the cyclotron frequency, sometimes the Lamore frequency. And just to remember, the magnetic force F is always perpendicular to the velocity because of that cross product. So as we'll show in a little bit later in more detail, the force cannot do any work on the particle because it's always perpendicular to the velocity. The radius of the circle is given by r equals v over omega, and so if we put in our these are all magnitudes, so if we put that into the r equation, so we'll put omega equal to this right here, then we have that the radius is given by mv over qb. So that's basically, the bigger the field, the smaller the radius, the faster the particle is moving, the larger the radius. And this is called the Lamore radius. So if v is not initially in the plane, everything we've said so far was in the plane, perpendicular to b, but suppose it's not perpendicular to b, then the component that is parallel to b does not contribute to the force. And that goes back to the v component crossed into b would, if it's parallel, is 0. If velocity is perpendicular to b, then we do have a force, and it's exactly the same force that we have above. So we have v parallel remaining unchanged, there's no force, whereas we have circular motion in the direction where we have v perpendicular. So as a result, the path is a helix. So let's take a look at that. So here we have B pointing down, and so if we look from the top, that would be like into the page. Okay, so if you look at the helix, you have at any instant a component of V which is parallel to the B field, and then you have a component which is perpendicular to it. So if you allow the particle to move along the B field, you would have no force on the particle, and it would just simply move parallel. If you only had the perpendicular motion, then you're going to stay in the plane and simply go in a circle. However, if we have both, then the particle will have uniform velocity in this direction. In this direction it will undergo the circular motion. And so this lousy helix which I drew by hand, at this instant here, or this position here, the particle would be moving in this direction. Here it would be moving in this direction. And so you combine this circular motion with this V parallel motion, and that gives you the helix. So if, again, looking down from the top, we would find that the radius for this normal velocity motion would be given by the same equation that we had before. mv perpendicular now divided by q sub b gives you that radius, and that's basically this diagram here for our perpendicular. And one more time, the parallel motion is totally unaffected by the B field, and so it just moves at a constant speed. If we add electric fields, then the combination gives us the Lorentz force. And so in a region where there is an electric field and a magnetic field together, the total force on the moving particle, this should be particle, is equal to F total equals F electric plus F magnetic. And we've already shown that the electric force is equal to Q times E, and here's the magnetic force which we've defined earlier. So taking this combination, this is called the Lorentz Force Law. And so it provides us with a connection between the total electromagnetic force acting on the charge Q. So if we have this combination, we have to realize that an important difference between the electric field and the magnetic field has to do with the fact that the electric field does work on a charged particle. It can accelerate it or deaccelerate it, and that means that it's going to be changing the kinetic energy, and therefore work has to be done. The magnetic field, on the other hand, does not do any work on the moving charge, and this is a direct consequence of the Lorentz Force Law. So look at the F magnetic only. Let's consider the differential of work equaling this dW magnetic due to a differential of displacement dl. So that's a vector dl. This differential of work done by the magnetic force would be equal to the force dotted into dl. Remember when we did the electric forces, we had E dot dl, but here we have the magnetic force. So yeah, one more time, if we use the E field, we have Q times this, times the E field. So if we take the magnetic force as defined, which is QV plus B, and take dl equal to V dt, so this is the increment of position related to the velocity and the differential of time. So putting those together, or substituting them into this equation, we have that dW magnetic is equal to what we have here. It's Q times V cross B dot V dt. Okay, but V cross B is perpendicular to V because of this cross product. The cross product is always perpendicular to both of these vectors. So as a result, we would have V cross B dotted into V is equal to 0. So what that means then is that the work done by the magnetic force, that differential of work, implies then that the magnetic field cannot do work. So here's the restatement of that. We conclude that the magnetic force can alter the direction in which a particle moves but cannot change its velocity. So how does an accelerator work? You put B fields in to bend the particles. Well, that's the point. It can bend the particles. You can make them go in circles, ellipses, or whatever direction and pattern of motion you want, but it cannot accelerate them. So an accelerator uses E fields to do the acceleration, and quite frequently that in a lot of accelerators, so if this is the path that this have, where this is maybe 6 miles around the circle, they'll have stations at particular positions where they do acceleration of the particle with E fields that is timed. So the E field is basically a pulse at the right time when the particle is ready for the kick. And so that's how accelerators work. So they use E fields to accelerate the particle, which is doing work on the particle, but the magnetic field allows the particle to sweep around the path. Okay, so one classic case is where you have a particle that you shoot into a non-zero B field. So let's take a case of a particle Q with a velocity v traveling along this axis. It enters a region where the B field is not equal to 0, and when we put crosses here, we mean that that's the tail of the vector B. So B is pointing into the page. Because of that B field and the fact that this motion is perpendicular to B, will stay in a plane. And in this case here, the plane is the plane of the page. And also the Q will undergo a deflection because it wants to go in a circle given by the B and the Q and the V. Okay, so if it were to undergo this motion, the distance A is the separation of the two regions, or the region where we have non-zero B. It will go in a circle, and that's equivalent to having a deflection D as it hits this region right here. So we have parameters A, D, B, and Q. And so the first question is the charge positive or negative for this particular deflection? And the second question is, find the momentum of the particle if we have these variables here, or these constants. So first of all, let's answer the question about the charge. Well, look at the direction of this deflection and use the right-hand rule. So B is into the page, V is in this direction. So you take V cross B and ask where the force is. And so if you have, let me redraw this, if you have B into the page and you have V along this axis, then you cross V into B, and so that will give you a force in this direction here. So that's what happens, that's the direction that this deflection is, and so that means that the Q is plus. So here we state it again, the vector product between V and B, V cross B, points upwards in the figure. And we got that by using the right-hand rule. If Q is positive, the force will be in the direction of V cross B, so therefore the charge of the particle is positive. Okay, so now let's look at the momentum, and so we'll look at the force again. And let's just take the magnitude because we know that V and B are perpendicular to each other. Then this simplifies into Q times V times B, and that's because V and B are perpendicular to each other, and so if you consider the sine of theta between the two, that would equal 1, and so you have then QVB. Now the motion of the particle being normal to the B field results in circular motion with some radius r. And the radius we can calculate because we know that the magnetic force is equal to the centripetal force, F centripetal. If you remember what that is, it's mv squared over r. R is the circular part of the trajectory of the charge q. Okay, so if you use the equation that we have here, namely this equals this, we can solve this for r in terms of momentum. And so just solve for r, and what you find is you have mv over qb. And we know that mv is the momentum of the particle. So very simply solve for p, and you get p is rqb, or qbr if you wish, for the momentum. So let's go to the same situation where we want to relate this deflection basically to a measurement scheme. And so if you consider this triangle up here, this distance is the radius, because that's the radius of the circle that this undergoes in the B field. And the angle theta is the angle between the vector r, which is where the thing enters, and this vector r when it leaves. And a, of course, is the base distance between the edges of the B field. So if we take that triangle, we can write it as r minus d squared, because that's this distance here, plus a squared is equal to r squared, and that's what we show here. Okay, so expand the r minus d squared, and that's shown right here. Add a squared to it, and that's equal to r squared. So you have r squared on both sides, so those cancel. You can rewrite this as 2rd is equal to d squared plus a squared. Solve for r, and you have this equation right here. Now the momentum of the charge can then be obtained by just writing qbr. What we're really doing is eliminating r from this equation. So if we write the momentum in terms of this r, we get this equation out here. So we have now the momentum as a function of this displacement d, and the rest of these things are constants. This is actually a useful equation because there's one type of mass spectrometer which actually uses this geometry to measure mass. So you have A and B fixed, the particle is accelerated to some potential v, and that gives the kinetic energy. And if you remember, the kinetic energy is equal to q times v. Kinetic energy is related to the momentum by just p squared over 2m. So what that means then is you can solve for p in terms of the parameters here, so you have 2mqv square root. So come back to expressing this in terms of the momentum, which we got last time, or last page. So that's equal to qb d squared plus a squared over 2d. Since we're looking for a way to measure mass, we solve for m, and it's right here. So it's a little messy, but realize that it has all the parameters that you can measure. So you have qb squared, the deflection appears here, the voltage that you apply to accelerate the charge is here. So measuring d yields the mass of this particle. And if you look at the mass spectrometers that use this technique, the size of these things can be several, well, let's say 2 or 3 meters in extent. What does that do? It just gives you a bigger deflection, and if you measure this extremely carefully, that gives you a good measure of mass. And I'm talking about separating isotopes, for example. Now, one thing about this is that you have to know the value of q. And of course the sign of q will change the direction of the deflection, and you don't want that. You want the deflection to be in a certain direction for a given magnet. Q in general is produced by taking a neutral atom or molecule and ionizing, usually by electron bombardment or laser bombardment. And so what you normally get, the largest number of ions are 1 times the magnitude of the charge on the electron. So for example, if you had hydrogen atoms and you ionize them, you'd get a proton, and that charge is plus E. So that's what we mean by this notation here. If it's a E is minus E, in other words negative, then this negative sign would flip it to a positive value. Do mass spectrometers ever measure negative ions? Sure, yeah. There's lots of cases. So for example, oxygen, it's not uncommon for that to be a negative ion. Another situation is what's called a Vigne filter. And if you look on Wiki, you'll find that a Evine filter is basically a velocity filter, and its purpose is to actually select velocities for charged particles. And this is actually useful in electron microscopes because you don't want a distribution in energy. You want to have a well-defined energy. Well, Willy Vigne is the one who developed this, and it was quite a while ago, 1898, and he used it for studying anode rays. So these would tend to be ions that are created at an anode. They were positive particles. The Evine filter can be configured to analyze charged particle energies. It can be used as a monochromator where you select one velocity and therefore one kinetic energy, or you can use it as a mass spectrometer. This is not all that common. So here's an example. We're going to use the above geometry that I showed you. We're going to apply an electric field in a direction to push the particle down so that the total deflection is 0. So we're going to balance the Lorentz force, which will give us 0 deflection. So for an electron, this would be an E field pointing up. So if you look here, we have the picture. This is the case where we had only a magnetic field. We get this deflection here. So if we want to counter that, we have to put a electric field in this direction. And basically the idea is to achieve this motion that just goes straight across like this. How do you detect it? Well, you put slits here and here, so that the only way that a particle can go here and here is if it goes in a straight line. And so if you have a detector here, as soon as you establish that equilibrium, you'll start seeing signal. So this is what you call the Vigne filter. So what is the relationship between the velocity when you have the match, when you have equilibrium? Let's consider B perpendicular to V, as we have used before, and we'll make the magnetic force put an upward force on the particle, and we'll let E be directed downwards to deflect the particle, and these are right in the opposite direction. So at balance, you have the magnitude of the magnetic force equaling the magnitude of the electrostatic force, and then you have achieved balance. So putting in our equations for the magnetic force, which is right here, the electric force, which is here, when we have this equal to the E balance, then we will have this equality. And remember that V is perpendicular to B. So what does that do? Well, that makes this V times B. And we're only interested in the magnitudes, so we get Q times V times B. On this side, we have QE here, and this should be E balance. So solve for V, and this is the relationship which gives you the condition where you have balance. And so what you've done is selected a V by the ratio of these two field values. Combine these results for B alone to derive the charge to mass ratio of a particle. So we go back to where we have E equals 0 and we measure the deflection. So that's sort of like the mass spectrometer case that we did before. So we're measuring D, and that's going to give us a parameter which we can use in the determination of Q over M. So E balance and B are the other two parameters, and A is given, so that's just something you designed into the instrument. So here we go. We start with the momentum equation where we have E equals 0. And so if you look at this, mv is d squared plus a squared over 2d times qb. We derived this earlier. So this gives us a d, but we've already talked about how the E field at balance over B times m, well, this is velocity right here. So m times v is equal to the right hand side. So then you can solve for Q over m, and that will be equal to E balance over B times this quantity here. Simplifying that a little bit, you have E balance 2d b squared d squared plus a squared. This is a measure then of the charge to mass ratio of the particle. Okay, so before people knew a lot about the atom, this was a fairly important measurement. Realize what you've got. You have a neutral particle which you ionize, and if you ionize it to just one Q, so one electron removed, or if you have an electron, then you can use this measurement to determine the charge to mass ratio. So in the case of an electron, that's called E over m. And Thomson was the first to do this, and for the measurement he received the Nobel Prize. The way he did it was he used a cathode ray tube, so this would be like the old television sets, with a fluorescent screen, and he measured the deflections and used the Vigne filter to establish this condition here, and was able to get Q over m. If you want to see some discussion of the history of that, you can go to this website. Okay, now realize when Millikan succeeded in measuring the charge on the electron, this was the oil drop experiment, that determined the mass of the electron. So for the first time, when those two measurements were done, a huge amount of knowledge was obtained by knowing the mass of the electron and the charge on the electron. Well, next time we'll continue to look at these forces, so may the force be with you, but this time we're going to look at the forces on conductors interacting with each other, for example.